Good afternoon, class. We'll now start the lecture on uh, flexural concepts in reinforced concrete design. So, is my audio clear?
Yes, sir.
How about my board, my visual? Okay. So, this uh, topic is not new to all of us here as engineers. We in one way or the other use the concept in dealing with the analysis and design of flexural members. Okay, so I'll discuss the topic very slowly first, and then if after some time I will stop my lecture, and then if you have some concerns, you may interrupt me. Okay, but please don't interrupt me while I'm still presenting the topic. I'll cut the lectures into subtopics so that we can actually address our concerns just in case. Okay. Okay. So the strength criteria is actually given by this formula. Always, this is the formula used for your strength criteria. Always your resistance. Okay. So this is the resistance is greater or equal to the loads. Okay, so this is the resistance R, and this is the load Q. Okay, so we know that Mn is a nominal strength. It's only an indicative value. It is not an accurate value, so we need to make sure that we apply some factors of safety, okay, which is more on the resistance. It's placed on the resistance, while the factor of safety here, Q, is actually the overload. Okay, so your Q here, which involves Mu, is actually your required strength, which covers some factor of safety due to overloading. So note that that phi, okay, so kulang ito. Phi is the factor to compensate for the deviation in the actual condition. And when we are talking of deviation, we are talking of material and geometric properties. A material is not accurate, geometry is not accurate. So, in one way or the other, we have to apply a correction factor, which is a capacity reduction factor in the form of phi. So, the concept of strength criteria is geared on the determination of the capacity. Okay, so our focus is more on the determination of Mn. Of course, if we know the nominal, we can get the design capacity just by multiplying it by phi. And this determination is actually given in terms of the basic assumption, uh, which is laid by the ACI on the compatibility of strain Okay, so when you say compatibility of strain, we are referring to this phrase, no? Plane sections remain plane before and after bending. And that is actually simplified in terms of describing that the unit strain above and below the neutral axis are simply proportional. In fact, it's linearly proportional. Okay, so this is linear. Okay, straight line. Okay, so compatibility of strain means this is straight, this is plane, this is before bending, and this is after bending. Okay. Okay, so this I will discuss to you this when we go to ductility. More of this. Okay, so this compatibility of strain is actually simplified on the basis of Bernoulli's principle, which of course exempt flexural members which are deep. So when I say deep flexural members, I am talking of the definition of deep beams here. Okay, so for deep beams, the compatibility of strain based on Bernoulli's concept is not fairly accurate. So we cannot apply this to deep beams. So this is now a typical strain stress diagram. So we often draw this when we were in college. Okay. So the distance from the compression, this is the compression fiber. This is the tension fiber here, the bottom, is actually divided in terms of the location of the neutral axis at the inelastic part. Okay, when I say inelastic, this is the plastic range in reinforced concrete. And this location is defined by the value of C from the compression fiber. Okay, C is sometimes also known as KD in your WSD. Okay, so this is the WSD language. Okay. Okay, so still remember that the KD, it's actually a percentage of the total depth, effective depth of your beam. And of course, your compression force is resultant is actually defined on the basis of Whitney's stress distribution, which is rectangular in nature, but in actual situations, this is normally almost very near to a parabolic. Okay, it's not a parabola, but it's very close to it. If you will look into the test conducted by the PCA, the Portland Cement Association, and the modified models by Hagnestad and so on and so forth. Okay, so we have now here the two diagrams which are needed to come up with the determination of the value of your Mn. Without this diagram here, we cannot solve Mn. So we need the strain and the stress distribution diagram. Okay, let's talk about a more uh, important, significant variable, which is phi. Okay, so this phi here is actually the curvature defined on the basis of your strain diagram, which is differently defined in your textbook when it comes to deflection. So basically phi is defined in your deflection concept as your what? Okay, m over ei. Okay, so this is the curvature. This is actually related to the moment diagram, and moment is related to deflections. Okay, so we take note of this definition of curvature But we will simplify the definition here first, taking note that phi is simply the angle between your strain, okay, strain uh, deformation all over a distance y from the neutral axis. So whatever strain is there, and then you divide it by y, is actually uh, equivalent to the angle phi, which is exactly the tangent of the angle. But for small values of phi, we can approximate that your phi is equal to tangent of phi. Okay? Because we don't anticipate very large deflection, your phi will come into very small values, and therefore it is accurate to assume that your phi and tangent phi are just the same. In radians, of course. Okay? And if we take note of the strain in terms of the curvature, it's simply the product of phi times y, where phi is the curvature, epsilon is the unit strain. And of course, y is the distance from the extreme compression, from the neutral axis to the strain fiber in question. So if the fiber is at this point, then your y is measured from always from the neutral axis. Okay, so for your second assumption, it is assumed that your steel is elastic, perfectly plastic material. So it's an elastoplastic material, which is again not true. In this case, there's what you call the strain hardening and the necking and failure state beyond the plastic range. So our assumption for reinforced concrete concept is that your steel is just a bilinear, okay? A bilinear plot of an elastic line and a plastic line. So this is simply uh, approximated in terms of a straight line that can reach a value of infinity. So this part here is no longer used, such that we will notice that your Fy cannot go beyond Fu. Okay? So in your RC, in your reinforced concrete design, you still have an Fu here, but we don't use this because the assumption is only up to the plastic part. That's why if Fs is greater than Fy, we only use Fy. Okay? And it is for the very reason that we want our member to be behaving as ductile as possible. That's why we do it this way. Okay? Not unlike in structural steel, we have the rupture strength, uh, which is computed on the basis of your ultimate tensile strength Fu. So for RC, we only have two lines. One is elastic, the other one is plastic. Okay? Perfect. Okay? Okay, so the third assumption, okay, take note, before we go to the third assumption, take note that the actual failure will be by crushing of the concrete in compression. Always. There's no tendency for steel to fail. It is only the concrete that will fail in crushing due to compression failure because of this assumption. Okay? Okay, for the third assumption, Take note that the concrete stress distribution will simply follow the stress strain diagram when you test a cylinder at the lab. Okay, so when you come up with a cylindrical specimen and test it in the lab, you get your FC prime, you have this stress path. Okay, what's a stress path? The stress path is simply this one. Okay, stress, string. So this is a lab test. So whatever is the shape of this will follow the shape of this. Okay, so this is stress versus distance. Okay, the distance is represented by a unit strain. The stress here is represented by the stress here. Okay, so that this is another assumption used by the ACI for flexural members. And the last assumption, if not the least, we can only use a maximum usable strain in the ACI as 0.003, but it can reach 0.008. Okay? In fact, the British code uses, I think, 0.004. Okay? So it can reach 0.008 due to redistribution. So this is again another topic we will be dealing with in case we have time. Okay, so where's that usable strain? This is the usable strain that I'm trying to refer to. This is 0.003. It cannot exceed this one such that at this point in time, this will stop. Okay, this will stop gaining additional strain in terms of analysis, of course, while your concrete location of the neutral axis will slowly what? Get smaller and smaller until such time that this part here will crash. Okay? So when the concrete in compression is no longer able to withstand the loading due to the very small area in compression, such that your moment reduces, okay, at a value less than the required moment or the ultimate moment, then your beam will fail. So that's how we look into the failure stages, considering the beam behavior. Okay, so we will be learning a lot of that when we go to curvature and ductility concepts. Okay, so for now, I'll stop at this point to just make sure that everything is still okay. If there are questions, you can ask questions and address your concerns.